All right. So first things first is we're going to talk a little bit about matrix inverses again. So we defined matrix inverses last time, but we didn't really talk about a way of calculating or finding the inverse of a matrix. So now I'm going to go ahead and give you guys an algorithm to find the inverse of a matrix, and then we'll also just go through an example of that. Okay. So first, the algorithm is as follows. So what you want to do is take your matrix A and augment it with an identity matrix of the same size. And then what you're going to do is you're going to perform row operations on it until you get to the point where you have reduced A to an identity matrix. And then whatever you end up getting on the right-hand side should be the inverse of the matrix A, okay? Now, if it's not possible to reduce A to an identity matrix, so this would be the case if you get a row of zeros when you are row reducing A. Okay. Then that would just mean that your matrix A was not invertible, okay? So now I'm just gonna do one example of illustrating calculating the inverse using this algorithm. So here we have a matrix A. It's gonna be a 3 by 3 matrix. 1, 1, 1, -1, 0, -1, and then 2, 3, 3. And let's say that we want to find the inverse of this matrix. So to do that, what we're going to do is, according to our algorithm, we're going to take the matrix A and we're going to augment it. In this case, we'll augment it with a 3 by 3 identity matrix. And now we're going to start row reducing. So I'll do the row reduction the usual way to start with, at least. So I'm going to use this one as a pivot and get zeros beneath it. So that should leave us with first row is unchanged. We should get zeros here. Okay. Row 2 plus row 1 is going to give me 1, 0, 1, 1, 0. And then when we do row 3 minus 2 of row 1, here 3 minus 2 is 1, 3 minus 2 again. Here we're going to have 0 minus 2. Here it's going to be 0 minus 0 and 1 minus 0. Okay? So all the row operations that you are performing, you want to be performing them on the right half as well. All right. So next, in order to make the left side look like an identity matrix, I want to make this entry a 0, but I also want to make this entry a 0 as well. So in addition to doing row 3 minus row 2, which is what we would usually do to get it to upper triangular form, we're also going to do row 1 minus row 2 to get rid of this 1. Okay. Now, fortunately, because we have a 0 here, these operations are not going to affect row 1 or row 3, at least in these entries. So we're still going to get 1, 0, 0. We should now have 0, 1, 0. And row 2 is unchanged, so I'm going to copy the rest of it down first. Okay, let's do row 1 minus row 2. So let's see here. 1 minus 0 is 1. 1 minus 1, 0 minus 1, and 0 minus 0. And then doing row 3 minus row 2. So that's going to be 1, negative 3, negative 2, and 1. Okay? And here we're almost done. We just need to get rid of this 1. So to do that, we have to use this guy as our pivot. So we'll do row 1 minus row 3. So when we do that, we finally get the identity on the left. And if we do row 1 minus row 3, it's going to be 3, 1, and negative 1. And so then finally, this will be what we ended up with here on the right-hand side. That should be the inverse of our matrix A. So there's an order of sorts, not like a super strict order, but you do want to do it one column at a time. So notice that I get all the zeros in the first column first. Then I move on and I try to get all the zeros in the second column. And then I move on to the next column after that. That's a little bit similar to elimination, where you start by working on the first column, and then once you get the zeros in the first column, you move on to the second column as well, right? The main difference is that here we also want zeros above the diagonal when we're finding the inverse, whereas when you're just doing elimination, you only care about getting zeros beneath the diagonal. Okay? All right. Now, I didn't have to do any in this example because I set it to be somewhat easy. But occasionally, you might need to swap rows, perhaps. In order to get a 1 in the diagonal entries, you also might need to multiply row by a non-zero constant. So like as an example, if I had something like, if I had something like, 2, 0, 0, that means that you would need to do an operation like 1/2 row 1 to get a 1 in that position, and in order to end up with an identity on the left at the end. So you might need to do these types of row operations as well during this process. Okay. I'll also say, so it's really easy to come up with an example of a matrix that won't have fractions in the inverse. I don't know if your professors will be kind enough to make sure that the inverse won't have fractions in it, though. So don't be surprised if your inverse is a little bit messy with some fractions. All right. But they're super nice. It's really easy, actually, to come up with examples without a fraction in the inverse. And I can reveal that secret to you guys later on this semester as well. All right, but that's all I really wanted to say regarding finding the inverse of a matrix. So for most of the rest of the review, I'm going to be focusing on the Ldu factorization and the variations of it and like applications of it, I suppose. All right. So I did do an example at the very, very end of my last review of getting an Lu factorization. If you don't recall, it's fine. If you do recall, I did a little bit with elementary matrices in order to get the Lu factorization. But now I'm going to show you guys like a quicker way of getting Lu factorization without having to down elementary matrices. Okay. So first, let's talk about what the Ldu factorization is. So what we're doing is we're taking a matrix A and we are writing it as a product of two matrices, L and U, where U is an upper triangular matrix. L is a lower triangular matrix. So it has zeros above the diagonal. Now, in addition to being lower triangular, L has a little bit more structure to it. So the lower triangular matrix L is also going to have ones on the diagonal, which is not necessarily the case for the matrix U. Okay. And to see how to come up with an Ldu factorization, I'm just going to illustrate with an example to begin with. Here is our matrix A, 2, 3, -4, -4, -5, 1, -2, 0, 6. Okay. So the first thing that I want to do is take the matrix A and just reduce it to an upper triangle matrix by doing elimination, as you usually do. So in order to reduce it to a triangular matrix first, I want to use 2 as a pivot. So what we're going to do is we're going to take row 2. And to eliminate the 3, we'll want to do -3/2 of row 1, okay? And likewise for row 3, if I want to eliminate the -4, we can do row 3 plus 2 of row 1 to eliminate that -4. Now, real quickly before I continue, if we just wanted to reduce to upper triangular form, there is something else that we could have done is we could have done 1/2 of row 1, because you might notice that really simplifies the first row. Okay. But specifically when you're finding the factorization, you don't want to do anything like that. Okay, so I'm just going to cross that out and exit. So don't do that for the purpose of getting the Ldu factorization. Instead, you have to only use these types of elimination type row operations. So just use what you have to start with to do the elimination, okay? If your numbers don't work out, that means you do have fractions involved, but you got to do that if you're specifically finding the Ldu factorization. So it's because when you do these types of row operations, the L is going to come from the elementary matrices that you use. And for the Ldu factorization, your L is going to be a little bit different and not necessarily even lower triangular, especially if you do some like row swap operations. So you really only want to do elimination type row operations to get an Ldu factorization with this like specific structure and the L in particular. Okay. All right. So then here, let's go ahead and carry out these row operations. So we should get 0, 0. Now if I do row 2 minus 3 halves of row 1, that should be -5 plus 6, which is 1. This would be 0 plus 3. Here we're going to get row 3 plus 2 of row 1. So 1 minus 8 will be -7. It's going to be 6 minus 2 is 4. Okay. And finally, I just need to make this -7 a 0. And so to do that, using this as our pivot, we'll do row 3 plus 7 of row 2. And that will leave us with, I will squeeze it in here. So 2, -4, -2, 0, 1, 3, 0, 0, and 4 plus 21 is 25. Okay. Let's see here, did I do that right? Or I think I made a mistake. So let me check. Row 3 plus 2, row 1. This would actually have been 6 minus 4. So actually, this should have been 2. And so if we do row 3 plus 7, row 2. Okay. Looks like it should actually be 23. Okay. And then I think that should be right. That looks familiar to me now. Okay, so this upper triangular matrix that we end up with, this is going to be our U for the Ldu factorization. Now, in order to get the matrix L, so it comes from the elementary matrices corresponding to these row operations. But you don't need to actually write out the elementary matrices to get it, because there's kind of like a shortcut, which I'm just going to show you guys. So we know L is lower triangular, and we know it has 1s on the diagonal. So I'm just going to go ahead and fill all of those entries in. Now, in order to get the remaining 3 entries, you can actually get them directly from your row operations. So specifically looking at the coefficients that you use here in the row operations, take the coefficients and just change the sign and place them in the corresponding entry of L. So here are the -3 halves that I have. I'm going to put a +3 halves in the 2, 1 entry. Here with the +2, I'm going to put a -2 in the 3, 1 entry. And finally, with the +7 here, I'm going to put a -7 in the 3, 2 entry. And so with that, that actually gets matrix L. And you guys can go ahead and kind of confirm it So try multiplying L and U together. You should see that, assuming I made no mistakes, with my row operations, this should multiply out, give you the matrix A that we started with. Okay. Okay. Now let's see here. Real quickly about the reason why that you change the sign of these numbers when you put them into the matrix L. Okay, so if you go back to the example that I did at the very end last time, we get the matrix L by multiplying the inverses of these elementary matrices together. And you might remember that when we look at the inverse of the elementary matrices, it has the opposite sign because it corresponds to the inverse row operation, if you recall. That's kind of why you end up doing the opposite of the numbers. Something else that I will also say is that if you remember that in previous problems or assignments, you had questions that asked you what were the multipliers that you used in your row operations. And you might remember the multipliers were a little bit strange maybe because at least with the way that I write my row operations, the multipliers were the opposite of these numbers that we are using. And you might remember that they use this notation for it as well for the multipliers. Now that we're going over the Lu factorization, you can see a reason why they use this notation, because these are actually the 2, 1, 3, 1, and 3, 2 entries of the lower triangular matrix L. Okay? All right, so any questions about what I've done in this example, at least so far? Okay, so in that case, I'll now illustrate a small application of the Lu factorization. Namely, let's take a look at how to apply the Lu factorization to solve a system of equations. Okay, so if you have an Lu factorization, you can use it to solve a system of equations a little bit more quickly. So first, let me describe the procedure for how you'll do this. So first, starting with the system of equations, which we will represent as ax equals b. If we have an Lu factorization for a, then a equals Lu. So I can replace a with Lu in this equation to get that. So now what we're going to do is I'm going to do a small change of variables here. So I'm going to write ux I'm going to replace it with the vector y so that I can rewrite this equation as simply Ly equals b. Okay. Now, what's going to happen is this. So we're going to take this equation, Ly equals b. And because L is lower triangular, we're actually going to be able to solve this equation using forward substitution. And so what's going to happen is you're going to solve for y, and after you solve for y, you're going to come back to this equation, ux equals y. And now, since you've solved for y, you can now use it in this equation to solve for x. And since u is upper triangular, you'll be able to solve for x by doing the usual back substitution. Since it's already upper triangular, so you don't need to do the elimination, all right? So I'll illustrate this using the example that we just did. Okay. All right, so the matrix A that we had previously was this. So I'm just going to write down for reference. So let's suppose that we have this system of equations. All right. And so we want to solve the system of equations. Okay, so of course we can write it in the form ax equals b, where x was the vector of unknowns, x1, x2, x3. And then b is the vector of the right-hand side. Okay. And I'm going to solve the system of equations using this procedure. So first, I'm going to need my L and my U. So let me go ahead and take my two results for L and U. I'm going to just copy them back down here for reference. So L was 1, 3/2, -2, 0, 1, -7, 0, 0, 1. All right, and then just also for reference, here's U. It was 2, -4, -2, 0, 1, 3, and 0, 0, 23. Okay, so the first step to solving the system using L and U was to solve the equation Ly equals b. All right, so here's the matrix L, and here's b. So I'm going to write out the system of equations corresponding to this matrix equation. So looking at the first row of L, the first equation is going to be 1 y1 plus 0 y2 plus 0 y3 equals -2. And then looking at the second row, it's going to give us the equation 3/2 y1 plus y2 equals, looking at b equals 1. Finally, looking at the last row of L, we have the equation -2y1 minus 7y2 plus 1y3. That's going to be equal to -1. All right. So because L was lower triangular, we already know y1. Now we're going to substitute it in the next equation. And then we can solve for y2. So let's see, y2 is going to equal 1 plus 3. So I think y2 is equal to 4. And then substituting y1 and y2 into the last equation. Let's actually write this one out. So -2 times 2 minus 7 times 4 plus y3 is -1. That's -32. Add it over. So if I did that right, y3 is, let's see here. What was that again? 32, 31, okay? Okay. Okay. So then now that we have y1, y2, and y3, we'll go back to the second step, which was solving the equation ux equals y for x. So we have y to give us the right-hand side, and then here's u to give us the left-hand side. So writing this out as a system of equations, the first row of u gives us 2x1 minus 4x2 minus 2x3 equals y1, which was -2. The second row of u gives us 1x2 plus 3x3. Let's see here, that should equal y2, which is 4. The last row gives us 23x3 equals y3, which was 31. Let's see here, did I do that right? Oh, okay, all right. And then from here, you can do back substitution to solve for x. So x3 is 31 over 23. So plug that into here and you can solve for x2. And then you can go back and solve for x1 as well. Since the numbers are a little bit messy, I'm not going to work through the rest of the problem, all right? But I'm sure by now you guys are familiar with doing back substitution. So I hope you'll forgive me for that. Okay, but just to recap the procedure though, okay? So you got the equation ax equals b, you replace a with Lu, and you think of ux as being a vector y. From there you can solve for y by doing forward substitution on the system of equations. Once you solve for y, come back to here to solve for the original x to get the solution to the original system of equations, okay? So any questions about that procedure? All right. Now that procedure of using L and U to solve a system of equations, It's going to be a little bit faster than doing like elimination on the original AX equals B. And in some applications, what happens is you have a matrix A, and as you continue like doing whatever it is that you're doing, you end up needing to use that matrix A and solving AX equals B for like multiple different right-hand side vectors B. So for a problem like that, having the Ldu factorization will make it decently faster to solve the AX equals B multiple times, as opposed to, say, having to do elimination multiple times as you get a new vector B and then have to go back and solve that equation, AX equals B, okay? All right. But anyways, let's continue talking some more about Ldu factorization. So right now I'm going to talk about some variations of it. So there's one variation of the Ldu factorization, which is the Ldu factorization. And so this is just factoring a matrix A now into a product of three matrices, Ldu, where L is still lower triangular with ones on the diagonal. Now in the Ldu factorization, U is upper triangular, but this time it also has ones on the diagonal. So in that sense, it's more symmetric, if you will, or at least it looks more symmetric. Then this matrix D here is a diagonal matrix. And so to get the Ldu factorization of a matrix, it's actually really easy. And so I'm just going to illustrate by, again, using the matrix A that we had in the previous example. And it's difficult for me to copy and paste, unfortunately. So I'm just going to continue writing down or recopying the matrices that we found earlier. So again, this was the matrix A that we had. And this is the L and the U from the Ldu factorization. Okay, now if you want to get the Ldu factorization, well, it turns out that this L is also the same L that you need for the Ldu. However, this U from the Lu factorization is not the same as the U that you need in the Ldu. But instead, what you're going to do is if you take this upper triangular matrix from the Lu factorization, which I'm just going to leave it as like the old U, because we're going to get a new one for the Ldu. Okay. What you can do using this old upper triangular matrix is take the pivots, so take the diagonal entries and put them into a diagonal matrix, just like that. That's going to give you the matrix D that you need in the Ldu factorization. Now, what you're going to do is take each row of this old upper triangular matrix, divide each row by its pivot, okay? So that means we're going to divide row 1 by 2, and we're going to get 1, -2, -1. We'll take row 2 and divide it by 1, so actually it remains the same. Then take row 3 and divide it by 23, so you'll get 0, 0, 1. And this new upper triangular matrix that you get, this is the U that you want to use for the Ldu decomposition. So with L the same as before, but with this D and this new U, if you multiply them out, you should again find that L times D times U is equal to A. And really, to understand how this works, just notice that if you multiply D times the new U, it gives you the old U. So if you have A equals L times, old U, and old U itself is D times new U, then of course it's still going to be equal to A. All right. So that's pretty much all there is to it for the Ldu decomposition. Okay. Or at least that's all that I'm going to say about it. So do you guys have any questions about that? All right. So next, we're going to talk about another variation of sorts on the Ldu factorization. So this is the Ldl Transpose Factorization or decomposition. You can sort of use those words interchangeably in this context. Okay, so let's talk about, so first there's something new that we need to talk about, which is the transpose. And then I also want to talk about symmetric matrices. We'll start by talking about the transpose. And so here I'm just going to make up a random matrix. I'll just do 1, 2, 3, 4, 5, 6. Okay. Now the transpose of this matrix, what you're going to do is take the rows, but write them as columns. Okay, so first row now becomes the first column in the transpose. Second row now becomes the second column when you transpose. And it might seem silly, but really that's all there is to it in transposing a matrix. So just take all of the rows and rewrite them as columns. That gives you the transpose, okay? Now, I won't go too much, certainly not right now. I might, towards the end of the semester, get more into it about why the transpose is important. But for now, what I will just make a note of regarding why the transpose is an important operation Okay. Let's suppose that we have two vectors, and to keep it small, I'm just going to work in 2 dimensions. Let's just suppose we've got these vectors u and v. So notice that if I take u and I transpose it, and then I multiply that with vector v, okay, so that gives me, transposing u makes the column into a row. So that's u transpose times v. When you do this matrix multiplication now, you see that gives you, u1 v1 plus u2 v2. And of course, you recognize that as the dot product of the two vectors. So this is one of the reasons why transpose is important, is because it sort of captures the dot product within the like operator transposing, if you will. Okay, or at least you got this connection between transpose and dot product. And so in as much as the dot product is important, the transpose is also important as well. All right. And then I guess I'll say another comment real quickly about transpose. So of course, as I said, the rows become the columns. You'll notice you can also think of it the other way, which is that the columns now become the rows. Okay? So 2 ways that you can think of how to transpose a matrix. Now I'll note a couple of properties about the transpose. So one property, if you ever have to transpose a sum, the transpose of the sum is the sum of the transposes. Okay. This one's probably not super important, but if you have a scalar applying a matrix and then transpose that, you can pull the scalar outside, transpose the matrix first, and then multiply by the scalar. Now, a more interesting property is when you transpose a product. So when you transpose a product, you can transpose each matrix individually, but you also reverse the order of them. So when you transpose AB, it's going to be B transpose first, and then times A transpose second. Okay? And then lastly, if you have a matrix A, which is invertible, then its transpose is also going to be invertible. And in addition to that, the inverse of A transpose is actually just going to be the transpose of A inverse. Okay? And I think it might be nice just to see a short proof of the last property. It's really short, so I'll go ahead and prove it for you guys just so you can see it. Okay. Okay. So if A is invertible, we know that multiplying A with its inverse will give us an identity matrix. So that was the definition of the inverse. Now what we're going to do is we're going to take this equation and we're going to transpose both sides of this equation, okay? Now here, when I transpose a product, I can use this third property to transpose the product. So it's going to be A inverse transpose first, and then A transpose second. And so that should be equal on the right-hand side. We have the transpose of the identity matrix. But if you guys think about it, what is the transpose of the identity matrix? So what happens if you take the identity and you transpose it? Can you guys see what you would get if you do that? Yeah, that's right. When you transpose an identity matrix, nothing happens, you get the same thing. So it's just equal to I still on the right. Okay, but now look at what this says. A inverse transpose. When you multiply with A transpose, it gives you the identity. What that tells you is that these must be inverses of each other, since they multiply to give you an identity matrix. So in particular, the inverse of A transpose is the transpose of A inverse. So like I said, it's a pretty short, pretty sweet proof, okay? So I thought I would just illustrate it. It's also a nice application of the third property that I mentioned. All right. And then something related to transpose is the notion of a symmetric matrix. Okay. All right, so a matrix A is going to be a symmetric matrix if it satisfies the property that A transpose is equal to A itself. Okay. So then you guys have already noted that the identity matrix is a symmetric matrix because its transpose is itself. Now, just to look at an example, let's suppose I wanted to see what a 3x3 symmetric matrix look like. Okay, so if I put ABC into the first row, since A should be equal to its own transpose, well, we know that in the transpose, the first row becomes the first column. So I also need to have ABC as my first column to make the first row agree with the first column, okay? Now let's see, I've used ABC, so next let's use letters D and E. Okay, so to be symmetric, the second row has to equal the second column for A to be equal to its own transpose, so this has to be E as well. And then finally, the third row and the third column have to match, but that doesn't really say anything about the last entry, so it could be anything. So this is the generic form of a 3x3 matrix. So what you see is that the diagonal entries could really be anything. but it has to be like symmetric across the diagonal in order to be a symmetric matrix, all right? So that generalizes to any size square matrix. To be a symmetric matrix, it has to be symmetric across the diagonal, okay? All right, any questions about that? All right. So now finally, I was going to talk about the Ldl transpose factorization. All right, so that factorization, it only applies to the situation where you have a symmetric matrix. So the way that the Ldl transpose factorization works for a symmetric matrix, it's actually really simple. So let's say you have a matrix A, which is symmetric. All you need to do is find an Ldu factorization for A. And the matrix U that you end up getting in the Ldu factorization, it will sort of automatically be equal to the transpose of L. So just get the Ldu factorization, and if your A is symmetric, the U will be equal to the transpose of L, and so that hence LDU is going to become Ldl transpose. All right. And so I'll just illustrate real quickly with a symmetric matrix as an example. So let's do 1, 2, -1. So therefore 1, 2, -1. We'll do 6, 0. So therefore 2, 6, 0 here. And then we'll do 3 like that. Okay. So as you can see, this is a symmetric matrix. It is symmetric across the diagonal. And so we're just going to get a regular LGU factorization. So to start with, we're going to reduce to an upper triangular matrix. So let's get rid of the 2 and the -1. Okay. That's going to give us 1, 0, 0, 2, -1. Okay. 6 minus 4 is 2. 0 plus 2. Row 3 plus row 1. So that's 2 and... Oh, really? Well, sure. Okay, that's another 2. That's not a big problem, I suppose. Oh no, that's interesting. So hold on. Let me think about this for a moment. Yeah. Okay. So let me adjust my problem because I don't want to get a row zeros. If I get a row zeros, that's going to break things. And so maybe I should. That's good to comment on as well. So also, only works if well, let's see here. Let's just say, in addition to A being symmetric, we also need A to be invertible for this to really work. Okay. Meaning that I can't get a row of zeros when I'm reducing to the upper triangular matrix. And well, I guess we'll see why when we do it, okay? So I'll go ahead and change one of these numbers to make sure that I don't get a row of zeros. So instead of 3, I'll just bump it up to 5, so that 2 bumps up to 4, okay? Okay, that's going to be better for us. Okay, so now I'm going to continue reducing to an upper triangular, so I'm just going to do row 3 minus row 2. So if we do that, we'll get 0, 0, and 2. All right. So this is the U in an Ldu factorization, all right? Now remember that to get the L, it's a lower triangular with 1s on the diagonal. And then looking at your row operations, take the opposite of these coefficients, or if you will, take the multipliers, put them into the corresponding entries of L, and that gets you the lower triangular matrix. And again, remember that this is for both, it works for both Lu and also Ldu. Okay, but to get the D and the U for the Ldu decomposition, so if you remember the procedure, it's take the U and Lu and divide each row by its pivot. So divide each row by its pivot. That gets you the new U. So divide row 2 by 2. Divide row 3 by 2. That's the U for Ldu. And then remember the diagonal matrix, you just take the diagonal entries of this U to form the diagonal matrix. Okay? And so as I noted, notice that since my matrix A was a symmetric matrix, notice that the U you end up getting in the Ldu decomposition is equal to the transpose of the L. So that's not a coincidence. That happens because our matrix was symmetric to begin with. So hence, instead of writing A equals Ldu, since the U is the transpose of the L, you can write it as A equals Ldl transpose. Okay? Then I'll go ahead and make a quick comment about me saying that A has to be invertible for this to work. So in order to get the new U for Ldu, the procedure is to divide each row by its pivot up here. But if you have a row of zeros, meaning you have a 0 pivot, you can't like divide this row by 0. So that's where that step kind of breaks down. And so you won't be able to get a U like this with ones along the diagonal for the Ldu factorization, okay? So that's why I say, that's why I put that requirement for A to be invertible as well. All right, do you guys have any questions about anything from that example? All right, so I guess I will end my review by finally looking at one more variation of the Ldu factorization, which is, I would say, a little bit more important than the LDU and the Ldl transpose that we just saw. Okay, yeah, 1 second. Small technical difficulties. Oh, okay. Let's see what just happened. Okay. Yeah, so I think my computer was just frozen for a little bit, but I think it's okay now. Are you guys still able to see everything? Just making sure that everything's good on your end. Can you guys hear me? Okay, great. All right. Okay. So yeah, I'm gonna talk now about the PA equals LU factorization, I guess. So when I was talking about getting the Lu factorization earlier, I said that you have to do the row operations in a particular way. Namely, you can only perform elimination type row operations. So I gave the example of not being able to just multiply a row by a non-zero number. But also for getting Lu, you also cannot do any row swaps, okay? So the PA equals Lu factorization. The P comes from the need to do a row swap in order to reduce to upper triangular form. All right, so if it's not possible, to reduce the matrix A to an upper triangular, without doing row swaps. So this would be the case, basically meaning that you have a temporary breakdown, okay? So if you can't reduce A to upper triangular without doing row swaps, then an Lu factorization of A is not going to be possible. But instead, you can get a PA equals Lu instead. And that P, that matrix P is a permutation matrix corresponding to the row swaps that you perform, okay? So we'll talk about how that works. Now, first things first, though, is it's going to matter when you do your row operations. So you do want to make sure that you do your row operations at the beginning in order to get the PA equals LU factorization. Okay. So if you don't do them first, if you do them last, you don't get an A equals, you don't get a PA equals LU, you get something slightly different. So just be sure you do the row swaps first to get PA equals LU specifically, okay? All right, so I'm just going to illustrate with an example. So here we have the matrix A, 1, 2, -1, -2, -4, 5, 1, -1, and 0. Now let's suppose that I just start to row reduce the matrix A to try to get an Lu factorization. So I would do row 2 minus 2 of row 1. But notice that if you do that, you are going to get a 0 in the next pivot position. That gives you the temporary breakdown. And in particular, you're not able to use the 0 pivot to eliminate whatever is beneath it. So this leads to LU being not possible, because we have to do a row swap to fix this situation. All right, so in order to fix the situation, we'd probably end up wanting to swap row 2 with row 3 to get this entry up here to be the next pivot. So what I'll do then is I'll go back to A, and I'm going to do the row swap first. Okay, so I see a need to do row 2 swap with row 3, so we're going to do that. So now we get 1 minus 2, 1. Let's see here. So row 3 goes here now. And then row 2 is the new row 3. Okay. Now, if I get the elementary matrix corresponding to this row operation that we did, this row swap, so remember, to get the corresponding elementary matrix, just perform the same row operation on the identity. So take an identity and swap rows 2 and 3. Okay. All right, so this elementary matrix corresponding to this row operation, that is the matrix P that we are looking for, okay? Now, if you remember, if I multiply a matrix on the left by an elementary matrix, the result is the same as performing the corresponding row operation. So in other words, this matrix that we have now, this is actually equal to PA. So now what we're going to do is we're just going to find an Lu decomposition for matrix PA. And that's how we end up getting PA equals Lu. So now we're going to reduce PA to upper triangular by doing row 2 plus row 1, row 3 minus 2 row 1. So adding these will be 0, 3, 1. This is 0. It's here, row 3. Let's do 0 again. -1 minus 2 is -3. Okay. So then here it's actually already an upper triangular matrix. And remember, to get the matrix L, we get it from these row operations. So again, L has 1s on the diagonal, 0s up here because it's lower triangular. Take these numbers and change their sign, put them in the corresponding place. We did not do another row operation because this was already a 0. So we're just going to put 0 in that entry, okay? So then with this L and this U, that gives us an Lu factorization for matrix PA. And that gives us the PA equals Lu. And I'm out of time, so let me just do a little bit more real quickly, and I'll wrap things up with that. So I would also like to just see how to apply this to solving a system of equations. So how to solve AX equals B, but using PA equals Lu instead. So it's pretty similar to before, just a small modification. So if we start with the equation AX equals B, what we can do is first multiply both sides on the left by P. All right, so then we can replace PA with Lu, since PA is equal to Lu. Then at this point, it'll work basically the same as before. So we're going to call Ux, call that a new vector Y. They're going to solve Ly equals PB using forward substitution. Once you solve for Y, go back to Ux equals Y. And you're going to solve this equation for X using backward substitution now, or just back substitution. Okay. And we'll just illustrate real quickly with the example that we have up here. All right, so let's say my B, I just make a vector for B, which is, I'll do 0, 3, 2. And so again, I'm focusing on solving the equation AX equals B for X. Okay, so the idea is we multiply both sides by P. Now remember that multiplying by P is the same as performing this row operation. So for vector B here, if I multiply by P, it's the same as just swapping row 2 and row 3. So I'm going to do that. So that's PB. All right, so then again, PA is the same as Lu. So then first what we do is we do Ly equals PB. Well, I guess I'll just write PB. So taking the lower triangular matrix L and PB for the right-hand side, this gives us the equation 1y1 equals 0 minus y1 plus y2 is 2. And then 2y1 plus y3 equals 3. And doing the substitution, y2 is 2. And then over here, y3 is 3. Now that we know y, go back to ux equals y. All right, so here's u. So using matrix U, we get the equation x1 minus 2x2 plus 1x3 equals y1, which is 0. Next would be 0x1 plus 3x2 plus 1x3 should be equal to 2. And finally, negative 3x3 should equal y3. And from there, you can solve for x to get the final solution to the original system of equations. And I think I get that. Okay. All right, so with that, I'll go ahead and end the review. So I'm going to just stop recording.